x over x plus 1, and it's asking you to find the critical numbers. So let's take this piece by piece. To find the critical numbers, what would you do?
Find the derivative.
Find the derivative. Set equal to 0. So I'm going to leave my numerator alone, take the derivative of my denominator. I said that wrong. Leave my denominator alone, take the derivative of my numerator, minus, leave my numerator alone, take the derivative of my denominator, all over my denominator squared. So when I do this, this is x plus 1 minus x. So I'm going to end up with 1 over x plus 1 squared. Two places for, so in order, when I have a rational expression like this, in order for it to equal 0, in order for this derivative to equal 0, the numerator has to equal 0. But 1 will never equal 0, so I have none there. No critical numbers there. Then I'm going to ask myself when the derivative does not exist. And that's going to be when this x plus 1 squared is equal to 0, which means x is equal to negative 1. So then when I make, so that it wants a critical number, so I found my critical number, I only have one critical number, it's when x is equal to negative 1. Then it says find the open intervals on which the function is increasing or decreasing and locate all relative extrema. So I am going to make the table. I'm going to put the negative 1 there. Pick a number less than negative 1. Let's say we use negative 5. Pick one more. Let's say we use 5. The two parts of this fraction I have is that 1, and then I have this x plus 1 squared. Well, this 1 is positive, so it's always going to be positive. Does that make sense? And then anything squared is always going to be positive. So my answers are always going to be positive. So what does that mean? What's my function always doing if my derivative is positive? So it's always increasing. But remember, at that negative 1, it's neither increasing or decreasing. It's a critical number. It's where the derivative does not exist. So I'm going to have to say negative infinity to negative 1, union negative 1 to positive infinity. You have to leave the negative 1 out. Now, since I don't change directions, there's no relative extrema. Good? Any other questions? Maria?
Can you just explain like the relative extrema a little bit more?
So if you have, so let's say I had I'm just making one up. So let's say I did this whole chart and I had negative 2 and I had 3, and these were my critical numbers. And then let's say when I did my derivative, I found out that this was negative, then it became positive, and then it became negative. So then it was decreasing, so it would be decreasing from negative infinity to negative 2. And then at negative 2, it switches directions and it starts increasing. So at negative 2 to positive 3, it starts. So if you think about it, your graph is going down, hits this negative 2, and then it starts going up. So what is that? So I'm going to have a relative min at x is equal to negative 2. And then I'm increasing from negative 2 to 3, and then at 3, I switch to directions and I start decreasing again. So I come here, I'm increasing, and then all of a sudden I hit this 3, x value 3, and I start decreasing. So the 3 is a relative max. They have to be the critical numbers. That was 5-1. They have to be the critical numbers. Which one was not the critical number? 18. F of x, 18. F of x is equal to x plus 1 squared, yes? X2 squared, then x plus 1? So you took the derivative of this, doing the product rule, yes? So you left this x plus 2 alone, took the derivative of that, which was 1. Then you're taking the derivative of this using the chain rule, so 2 times x plus 2 raised to the first power. Derivative of what's inside is 1, and then times x minus 1. So here, I get x plus 2 squared, and then plus 2 times x plus 2 times x minus 1. Did you factor out an x plus 2? So if I factor out an x plus 2, I'm going to have a bracket. Here I'm left with 1x plus 2. And then here I'm left with 2 times x minus 1. So do we agree that this is x plus 2 plus 2x minus 2? So then this is x plus 2, and then this becomes 3x. So I'm setting this equal to 0. So here x is equal to 0, x is equal to negative 2. Where does it, I'm just pondering for a second. So my derivative is my parts of my derivative are 3x and x plus 2, yes? And then I did my answer. And then you pick something less than negative 2. Something in between, something more, yes? So negative, negative, positive. Negative, positive, negative, positive. I don't know why I'm keeping going on. So it's increasing from negative 4. Oh, no. I made that fault. Negative infinity to negative 2. Yes? And then at that point, I start decreasing. So from negative 2 to 0. So I'm increasing, then I start decreasing. So this 2, negative 2 is what? Relative max. Really? I'm going to have to. It is. And then, so I'm decreasing, and then I'm going to start increasing from 0 to positive infinity. So at 0, I start going up. So 0 should be a relative min. Numbers, if any, and then find when the function is increasing and decreasing, then locate all relative max or min. So you're just going to have to say whether it's a max or min. That's it. Okay? Okay. First thing I have to do is take the derivative. That's like the first thing you should always do. So here I'm going to have 2/3 times x minus 1. Subtract 1 from the power, so this will be negative 1/3. Take the derivative of what's inside, which is 1. I like writing it so it's nice and pretty. So I like knowing that 2 is in my numerator and the 3x minus 1 to the 1/3 power is in the denominator. That just makes me feel better. Then what do I do with that derivative? Set it equal to 0. So I'm going to set it equal to 0. So now there's 2 places that I can find critical numbers. One is when the derivative is equal to 0. In a rational expression, the only time it's equal to 0 is when the numerator is equal to 0. So 2 is equal to 0 will never happen. So there are no places where the derivative is equal to 0. Which, I hate to say always, but I'm going to say most of the time. When you have this situation here where your derivative is never equal to 0, you're not going to have that bump. Are you with me? You're not going to have like a curve, which means you're probably not going to have a relative extreme. All right, moving over. So now I'm going to do this one. I'm going to say, when is my derivative? So now I'm going to set this whole thing equal to 0. Technically, I'm dividing by 3. So that's still x minus 1 to the 1/3 power is equal to 0. How do I get rid of that 1/3 as an exponent? Yeah, so technically I'm raising both sides to the 3rd power, but it's 0, so it doesn't really matter. So I'm going to have x minus 1 is equal to 0, so x is equal to 1. Yeah, it's the place where the derivative and the function is undefined. So technically I have a vertical asymptote there. So that's okay. That's still going to be like a critical number. It's still going to change. It might change the direction of my graph. So, bad. So I'm going to put a little dot there. Pick something less than 1. Pick something more than 1. Now I take the numerator, which is a positive 2, so that's going to have absolutely no effect. And then I take 3 times x minus 1 to the 1/3. Oh yeah, 1/3. I'm good. I had a little heart attack there. So if I put in 0, this 2 is never going to change, right? It's always going to be positive. So when I put in 0, I'm going to have -1 raised to the 1/3 power, which is going to be negative. So my whole answer is going to be negative. Then I'm going to have 2 positive. So the whole thing is going to be. So then I am going to have decreasing to the, it wanted this, yes? Decreasing from -infinity to 1, increasing from 1 to positive infinity. So do we need a visual representation? We're going down, 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 then we're going to go up, up, up. So what is that 1 going to be? Relative min.
Did you just say that?
I said sometime, but well, here's why this one does it, is because this is an odd root. Does that make sense? Even roots. See, I said as soon as I said it, I said, oh, I probably shouldn't say it, but I did. I went ahead and said it anyhow. Moving on. Yes, sir. Because there's only one critical number, so it's only dividing my interval into 2 spaces. Yes. And then now you have example 5, yes? Do you want a second to do that one on your own?
No, I got it.
Am I going? I feel like I do all the work. All right. Take the derivative. I'm going to leave my denominator alone. Take the derivative of my numerator, which will be 2x. Minus, leave my numerator alone. Take the derivative of my denominator, which will be 2x. And this is all over x squared minus 9 squared. Can I factor out a 2x in the numerator? Are you okay if I do that? I guess I really don't have to, but I kind of.
Cancel out.
They will eventually. Well, they don't cancel out now. They will when they become 2x cubes. Okay. Oh, hey, it was just an idea. A bad idea, apparently. Do we agree that's what I get when I multiply everything out?
Yep.
So then we agree that this will be. Never made that mistake. So we agree that this is negative 18x over x squared minus 9 squared. So when is my derivative equal to 0? What am I going to set equal to 0? Negative 18x is equal to 0, so x is equal to 0. That's one critical number. And then I'm going to have x squared minus 9 squared equal to 0. So x squared minus 9 is equal to 0. Because technically I took the square root. Yeah. Then I'm going to add 9. X squared is equal to 9. So x is equal to plus or minus 3. So I have 3 critical numbers. 3. Well, that's a lot. Is that not a lot? Let's try a different color. Negative 3, 0, and 3. Okay, who wants to pick the test points? Negative 4? 6. Okay, that was kind of aggressive. All right, negative 18x, yes. And then, x squared minus 9, but it's squared, is it not? So do we want to cheat?
Yeah.
If something's squared, what kind of number is it always going to be? Okay, that's my cheating. That's not really cheating. What? Common knowledge. So when I put in -4 and -10, so this will be -18 times that -4, so this will be positive? Positive. When I put in, okay. So, it is, do you want to do decreasing first or increasing? Decreasing from 0 to 3, union 3 to positive infinity. Remember, you have to leave that 3 out of it. Increasing from negative infinity to -3, union -3 to 0. Now you have 3 critical numbers I have to check for relative max or relative min. This one, this -3, since I'm increasing, and still continue the increase, is there going to be any relative extreme at -3? No. 0, I have a change in direction. I'm increasing and then I start decreasing. So what is 0? So 0 is a relative max. And then when I hit my next critical number, decreasing, stay decreasing. No relative extrema there. So this would be my whole answer. There's no relative min. No. The only time you have to write none is if there's no relative extrema at all. And did anyone graph it? Just for the fun of it? Yes. You have to leave out the 3. So, I'm not even going to say it. I think it's more writing. I don't like that. All right. So we all agree that we're taking a test next class, yes? So I thought I'd go over everything that is on the test in my way, this way.
Wait. Is it 5 points or 5 points? Oh, how many points?
You know, I haven't done points yet.
Why did you make it 100 and scale it down? Yeah, why did you scale it down?
Because when I not yet, in a minute. So 5.1 introduced the concept of minimum and maximum on an interval, on a closed interval, and on an open interval. Then we did the extreme value theorem. Does anyone remember what the extreme value theorem said? The extreme value theorem said that if you are in a closed interval, then you are guaranteed to have an extreme max and you're guaranteed to have an extreme min. It's when you have the open interval where you have one side that isn't. So a closed interval goes from like 3 to 7. That would be a closed interval. You're guaranteed to have an extreme max and extreme min. Do you remember how you find those points that you check for your extreme max and extreme min? You test the endpoints and then you they find the derivative, set the derivative equal to 0 and look for any relative max or relative min. We'll practice. But if I have this, if I have a closed interval, I'm guaranteed to have a max, I'm guaranteed to have a min. It's when I do something like this, where I have an open interval, so that 3 isn't included, I may not have a relative max or a relative min. That was just like a couple days ago that we did that. Okay, and then we talk relative max, relative min, and then critical number. Everyone remembers those words, yes? So the problem that you had is like locate the absolute extreme on the functions on the closed interval. So I'm between -1 and -2, which means I will have an absolute max and I will have an absolute min. Now, do you want to go to the whiteboards and do this? Okay, go. All right, this one, we took the derivative, we set the derivative equal to 0, we got these two critical numbers of 0 and 1. So then I take the endpoints, these are the endpoints, and then my two places where the derivative is equal to 0, and I put them back into the original equation, I find the highest y value and the lowest y value. So this 2 would be my max, and that's the y value. The 2 is the y value. That's my max. The negative 5/2 is my min. And everything's great and wonderful. I'm guaranteed to have a max and a min because I was on a closed interval. If I were to change this problem ever so slightly, and I made my interval from -1 to 2, and now I'm leaving that -1 out of it, it is no longer a closed interval, right? It's an open interval because I'm not including that -1. And because that -1 has my min, this interval would have no min because the min has been taken out of it. If it were the 2, if it were this way and I had the -1 was included and the 2 was not, then there would be no max. And then if it were on the open, yes. Yes. If the zero were, if one of these critical numbers were either the max or the min, then me changing these intervals would not change that being a max or a min. Okay, next one. So this one, so this is the same thing that I just explained. So since we're running out of time, can I skip it? If we have time, we'll come back to it. Okay. 5.2 is when we introduced Rolle's theorem and mean value theorem. And I feel like you guys are still on the struggle bus with this. So here we go. 3 conditions for Rolle's theorem. What are the 3 conditions?
Continuous.
Continuous.
Has to be differentiable.
Differentiable. And then f of A has to equal f of B. So this has to be continuous on the closed interval, and it has to be differentiable on the open interval. In other words, if you cannot find the derivative at the endpoints, that's okay. Then what happens if you meet these 3 things? What does Rolle's theorem tell you? What can work? What that means is that if you take the derivative of the function, it should equal 0 somewhere in that interval between A and B. That's what Rolle's theorem says, which is not to be confused with the mean value theorem. What are the 2 conditions that have to happen for the mean value theorem? Continuous on that closed interval, differentiable on that open interval, and then what this one's saying is if you take the slope of the secant line, then somewhere your derivative should equal that slope. Yeah. That one? Okay, fine, whatever. Okay, good? So now let's do one. Determine whether Rolle's theorem can be applied, and then if so, do it. You can go to the whiteboards. Okay, this one we asked ourselves, is it continuous on the closed interval? And we said yes. Is it differentiable? We said yes. Then we put -8 and 8 back into this original equation. We got the same value. So that tells me I can do Rolle's theorem. I take the derivative. I set the derivative equal to 0, and I get x is equal to 0. So that's going to be my critical number, my c value when the derivative is equal to 0. And that 0 is in the intervals -8 to 8, so it works. The next one, we're going to determine whether the mean value theorem can work. So I'm going to say, is this function continuous on the closed interval from -1 to 1? And I'm going to say yes. Is it differentiable from -1 to 1? And I'm also going to say yes. Okay, I have to control the crowd. Easier to distribute the x and then take the derivative, yes? So I distributed the x. Now I'm going to have 3x squared minus 2x minus 2. Yes? I'm going to set that equal to 0. And now I have to product sum, do I not? So the 2. It's not factorable, is it? Huh? Oh, my bad. Stop right there. My bad. Oh, and I recorded that. That's so bad. All right, so here I have my derivative. I'm just going to let it sit there. Now I'm going to have to find the slope of the secant line because I'm doing mean value theorem. So this is the slope of the secant line, yes? Secant line. So now I have to find f of -1 So f of negative 1 is equal to 0. F of 1 is equal to negative 2. So now I'm going to take the difference of the y. So I have this ordered pair, negative 1, 0. This other ordered pair, 1, negative 2. The difference of the y's over the difference of the x's. So this will be 2 over negative 2, which is negative 1. So then I'm going to take my derivative, and now I'm going to set that equal to negative 1. Pardon me? So I set my derivative equal to the slope of the tangent line, or the secant line, which was negative 1. So now I'm going to have 3x squared minus 2x, add 1, minus 1 is equal to 0. Now I can product sum. It was minus 2, but I said it equal to minus 1, so now I'm adding 1 to both sides. Product summing, do you guys, do I have to go over product sum? So here I'm going to have 3x plus 1 is equal to 0, x minus 1 is equal to 0. 3x is equal to negative 1, x is equal to negative 1/3, x is equal to 1. Are both of those on the interval? Are both of those in the interval? Yeah, but is one an endpoint? This one's an endpoint, so I'd probably toss that one out, and then I'd say c is equal to negative 1/3. So remember, if it asks you for the slope of the secant line, I found it. The slope of the tangent line is this is when the x value when it's equal to the same. If it asks you for the equation of the secant line, you would go back up here, the equation of the secant line, you said your slope was negative 1. You would pick one of these ordered pairs, doesn't matter which one. So let's say I use this one. I'm going to say y minus 0 is equal to my slope times x plus 1. So y is equal to negative 1 times x plus 1. And I could leave it like that or distribute to negative 1. Good? If it wanted the slope of the tangent line, here I know my slope is equal to that negative 1. I know my x value is negative 1/3. How would I find my y value? I'd have to take that negative 1/3 and plug it back into the original equation up here and find my y value. And then write the equation of the tangent line from that. Hopefully I'll be nicer to you on the test and it won't be a fraction. No promises. Huh? It is long, but we're in calculus. Huh? I can't, yeah. Can someone do f of negative 1/3 for me, please? I'll pause while you guys. So then I'm going to do y minus 0.52 is equal to negative 1 times x plus 1/3. Okay? Good?
Wait, that's the slope of the tangent.
No, this is the equation of the tangent line. Yes? Of the review worksheet? No. It's not going to happen either.
Why?
Okay, 5.3 is what we just did, increasing and decreasing. That's where you make the table. The first derivative test is where you decide whether you have a relative max or relative min. We just went over those, so we're good on those, yes? I have one, though. Here you go. There you go.
Is this like how all the reviews are?
2, 3, 4. All right, so critical numbers, if any. So I'm going to set the derivative equal to 0. So this will be 6x squared plus 6x minus 12. So I am going to factor out a 6 and make it x squared plus x minus 2. And if I product sum that, that makes that x plus 2, x minus 1. And that's my derivative. So my critical numbers are when my derivative is equal to 0, so when x is equal to negative 2 and when x is equal to positive 1. Everyone's good with that, yes? Then the next thing it wants to do is I'm going to decide when it's increasing or decreasing. So I'm going to make my little table. I'm going to put in negative 2. I'm going to put in 1. Pick test points. Let's say I do negative 3, 0, and 4. When I go to make the left side of the table, I'm using everything that made up my derivative, so these three things. the 6 isn't going to change the sign because the 6 is positive, but you might want to get in the habit of writing that 6 in case, because if it were negative, we would switch the signs. Does that make sense? Okay, so here I'm making my table. Oh, I didn't make that little dot. So 6 is always going to be positive. Then when I do, when I put in -3, it'll be negative, negative, and negative times the negative will make it a positive. When I put in 0, this will be positive, negative, the whole thing will be negative. When I put in 4, everything's positive. So I am decreasing from -2 to +1. Okay, so we said it's decreasing on the interval from -2 to 1. It's increasing on the interval from -infinity to -2, and then again from 1 to infinity. Then to do the first derivative test, I'm going to decide when I have a relative max or a relative min. So at this -2, if you think about it, your function is increasing, increasing, increasing. You hit this -2, and then you start decreasing. So that's going to be a bump up, so that's going to make it a relative max. Then I'm decreasing, decreasing, decreasing. I hit this 1, and I'm going to start going up. So that's going to make this 1 a relative min. All right, so your homework is the 5.1 to 5.3 review worksheet, and I will see you next time in class.